Great. So I think we are live. We are global, and I'm very glad to have Professor Noga Alon for this live. So I have mentioned, some of the awards, etc., that he had, like a Dijkstra Prize, Gödel Prize, ACM kind of like his, and Shaw Prize, and among lots of other awards. But here I want to start with some, personal stories actually. So I think it was summer of 2004 or 2003, I believe, that I was an intern at Microsoft Research. And at that time, it was supposed that, we are giving some talk. And I think like this was a joint talk, actually. Eric Demain was there, and he was giving the talk, and I was there. I think part of it maybe it was my talk as well. And we had the paper, we just submitted, and at the end, Eric actually mentioned some open problems that we don't know the answer. Just after the talk, and Noga came and said, okay, I solved that problem. It was like amazing. And we had actually lots of discussion with Noga and Eric. That's a few days that Eric and Noga were both at Microsoft. We were talking about several research stuff. And one thing that, Noga was already a professor, well-known professor at that time, and I was like an intern student at MIT. And it was actually one thing that I caught my eye. Like, he's actually very humble. And he has lots of papers, like I think 600 papers. We talk about that and the way that he's so productive. But also he has been very humble. We had, I think, that paper later. He also, that was interesting that he had written up actually everything that we discussed and sent us to us. Oh, this is the proof that I have written it formally. That it was also very interesting that, like he had written everything. Later we had, I think, another paper about network. This was about some embedding paper. Then it was some network creation. I think that was a direct something that came to Tom Layton, to Graham, and I think he mentioned the problem to you, or Fanchang mentioned the problem. But anyhow, but during this year, I think I was really amazed by the knowledge and the humbleness of Brother Noga Alon. And this is like all the time, I will say, probably, I don't know any person who has the knowledge in combinatorics, especially, and the graphs that Noga had it. Anytime that I had a problem, I just emailed him some question, and just a few hours, sometime later, I got the answer. And it was amazing. It was something about the RS graph, for example, later happened, or others. And yeah, so that's the thing that I thought that would be, great things. And of course, he's already, very well known. And we will talk about, some of this. And like all the, way that he's, so productive, I think. Probably, we have the Erdos number. We may have, maybe in the future, Alon's number. In that case, I will be happy, to have the Alon number one. But having said that, yeah. So let's start, with Noga. Do you want to say a few words? Starting, then we are asking, some questions. We discuss about life research, everything.
Sure. Yes. So thanks, Muhammad. It's a pleasure to be here, and I'm really impressed with this initiative and how much time and energy you invest in it. I should say, by the way, so I remember that collaboration in some almost 20 years ago. And I should say that these things that sometimes happen when you hear a question and it's just very similar to things you know, or to things that you've thought about. So some people sometimes may find it impressive because it looks as if you are kind of solving a problem instantaneously. but really the reason is often that you just thought about something very similar before, and therefore it comes naturally.
Yeah, again, thanks. But I think the question that I have asked, I can remember that they were not that trivial. So surely I think it is the unwellness that you will say that. But yeah, I mean, of course, I mean, your knowledge. I think that's the part that I mentioned actually at the first, that I think you have a very good knowledge about the whole combinatorics. That is, I have not seen in anyone else that I can say this level that, especially, I mean, there are, of course, I mean, there are different fields, but I think in the graphs or others, like I was truly impressed in that thing. Great. So I think having said that, let's start, I mean, from the beginning. So I think maybe you want to talk a little bit, I mean, when you were a child, essentially. I think you have been born in Haifa. And then, I mean, when you were a child, I mean, did you like math? How was like or this was like later you became math? That's how you started with math. Then, I mean, you have done several papers actually in computer science. I think you have 84 soda fox stack papers, and I mean, especially the stack fox paper are like actually quite large. And I mean, like in terms of papers, I think as a content that last time, I think last week, maybe it changed, actually increased for now, 423 journals and 176 conference papers. And I mean, a book that you have the probabilistic method and with Joel Spencer. So these are the things that, I mean, you have it now, but I mean, when you were a child, have you considered that? I mean, talk about a little bit about your family, etc. And then, yeah.
Sure, yeah. So I can, I should mention, by the way, that the numbers of papers are not, is not such an important, I mean, this more says about the way a person works, and some people write more, some people write less. It's more important what you write and what you do, and not only the numbers, but of course now in the internet era, it's so easy to get all these statistics immediately about numbers and citations and everything. So this is what we tend to do. But let me talk about childhood. So really, I knew very early on that I'm interested in, it was more mathematics at that time, maybe computer science was less developed. And of course, maybe I had my own opinion as a child about what it is to be a mathematician, which maybe does not have very much to do with reality. But still, I was always very interested in solving puzzles and in reading about the history of mathematics. So I think that really since elementary school, I was interested in mathematical puzzles, and I thought that this is what I want to do. Although maybe I didn't know exactly what it means to be a mathematician in academy. And I think that one thing that appealed to me was this objective nature of the subject, that somehow there is this absolute definition of truth. I mean, something that is correct is correct, and you cannot argue about it. And I think that this was something that I always liked. Yeah, actually, one story that I had from an early age, and you know, I have been telling this story already maybe twice or three times, so I'm not completely sure now if what I remember is exactly how it was, or I remember how I'm telling it, but still, I think it's pretty accurate. And that was when I was 11 or 12 years old. My parents had some people visiting for the Eurovision song contests. So there was this song contest, and several countries participate. And then the way it goes is that every country is voting, and according to the votes, then there are the results.
Yes.
And the friends of my parents, they wanted to amuse themselves, so they tried to guess the final ordering. And each person gave his or her ranking of what they think the final ranking would be. And then afterwards they heard the results, and they decided to give a score to decide who was closest. And this was basically what they do was the L1 distance between the guessed ranking and the actual ranking. So
yes.
if some country was number 3, and I guess that it was number 2, then it gives an error of 1 and so on. And we sum the absolute values of the differences over all countries.
Yeah, so I think to just give an idea about the L1 differences, that you are just putting this down essentially in 2 lines, essentially, and you will just compute what was the correct ranking, what was your guess ranking, what is the difference, and you will sum it up overall.
That's right. So you sum the absolute values of the differences, right? And then, so they did the computation, and they found out that every score was an even integer. But, and then they started to discuss, so I was in the other room, I was not, and they started to discuss if this must be the case. And my parents were not mathematicians, but my mother had always a very good mathematical intuition. And she said she's convinced that it must be even, but some guy there who was actually an engineer, he said that not, that it can be odd, and he's willing to bet. And you know, they had this discussion, and finally my mother said that let's call Noga and ask him. So she knew I'm interested. Okay, so I came. I was a relatively small child, but. And they told me the problem, and I thought about it, and indeed it's not so difficult, although maybe then they had to think, it's not so difficult to see that it has to be even.
And you are talking about the sum should be even.
About the sum yes, of absolute values, yes. And the reason is basically because if you take the sum with no absolute values, then it is 0, because it is the sum of all the ranks minus, again, the sum of all the ranks. And when you change a number from minus to plus, then you change it by an even number. So this basically is the argument. And I was happy to see it, and I kind of told them. But the nice thing, so I'm saying it not because I was so proud. I mean, it's not a difficult thing, but I was able to convince this adult, this engineer, that indeed this must be even. So I kind of showed him the argument, and he agreed, and he really said, you know what, you are right, I was wrong. And I think what impressed me, you know, usually when you argue with someone about politics, I don't know, I mean, it's never the case that party A is telling party B, you are right, I was wrong. I mean, we all get more and more convinced of our original opinion.
Yes, exactly.
Because, but in mathematics, it's different, right? I mean, you can prove, and even if you are a child, a 12-year-old child, you can convince a grown engineer, and he will admit at the end that you are right. So I think this is one thing that I always liked about mathematics or science, computer science, that things have an inherent truth, and you can convince someone about some validity of some statement, and this is one thing that I liked about the subject. Besides, of course, the elegance and the challenge and the fact that it's interesting.
Yeah, actually, I think this is a very great point, and this is somehow unique to math. Even you mentioned about social science like politics, others, but even like a regular science also. I mean, we see Hubble, like this James Webb and other things that we get it. I mean, we get something. This is our thinking of the world essentially. But I mean, there is no proof that it should be like that. Or I mean, the quantum. I think we were talking about quantum, and we were talking with Professor Peter Schwartz. Said, okay, maybe next time there is something that is doing it more complicated and can say quantum and other type of mechanics that we have. But in math is somehow the only one that you can be really convinced this is the proof, and that's it essentially. So
yeah, this is right, because everything is completely rigorous. There are definitions, and we are not in physics. You are trying to understand how the world behaves. So maybe we learn quantum mechanics. Maybe the way it actually behaves is a little different, or maybe a lot different than what we think. But with mathematics, we just have to be consistent with the axioms and with the logic rules, and therefore the notion of truth is completely well defined.
Great. So yeah, so I think you answered actually very nicely this one with starting with a very good intuition about math and the difference with others. So have you participated in any math competition? I think it was the IMO at the time that you were. I think it was a long time ago.
Yeah. So what happened is, so in Israel there were two main mathematics competitions for high school. And I won both, indeed. So one was being organized by the Weizmann Institute and one by the Technion, but this was just national. And unfortunately, at that time, Israel still didn't participate in IMO. So I graduated from high school in 1974. And I think Israel started a few years later, which is a pity because I think I liked it and maybe it would have been interesting to
yeah, I think it having that. I mean, that was interesting. That like have the. So I think you got your PhD also in 1983. So I think that was at that time. I think had that because I was talking with Professor Peter Schwartz. I mean, he actually participated in he had a silver medal in IMO. I mean, I had it later, of course, much later. I have it in IOI, a silver medal. But I think having that actually is a good one. Like anything that motivates me is just that one, that I have achieved something in my high school years that continued after that. Great. And do you want to say, I mean, what about your family? Do you have your children? Did any of them took the math way, or like grandchildren, or you try to convince them, or you didn't even try to convince them? So yeah.
Yeah, no, definitely I didn't try to convince. Let me also mention, by the way, another thing that maybe influenced me as a child is that already in the end of high school, I met Paul Erdős. So he used to visit Israel quite often. He had this kind of permanent visiting position at the Technion. And so he would come often, and the secretary in the math department at the Technion was a good friend of my mother. So really I met Erdős when I was still a teenager. And he asked me, so we had some discussions. It was quite influential. Now about my family, so I have three daughters. They are all grown, so we started very early. So I was a young father, and my eldest daughter, she studied first degree in mathematics and computer science, but and she worked a little bit in high tech, but afterwards she did a second degree in business school, and she's not really in academia. I never tried to influence, and in fact, I was a little bit surprised that this is what she chose. I mean, I knew she was good, but she was never kind of really extremely enthusiastic about it. So I was, but she was good. My other daughters are not. I mean, now they are all in some sort of high tech because this is what people are doing nowadays. But they didn't go to academy, and they are all married, and we actually have already 7 grandchildren. So that's That's great. The youngest is just half a year old.
Yeah, congratulations. Actually, I have my daughter is like 9 months old as well. So of course, like a being parent is one level closer to the difficulty. But yeah.
Sure, yeah. But you are right. Yeah, but I learned. So my parents always. So as I said, my parents are not in academia. My mother studied history, but basically, and was also a writer, and my father was a businessman, basically. But they always encouraged me and my brother to do whatever we like. I think this was very important. So they kind of told us that it's important to do things seriously and to like what you do, but you can choose anything that you like to do. They never tried to force us in some directions that they thought would be more practical or whatever. And the same, and this was my behavior with my daughters also. And I think they are doing well.
Yeah, I think that's a great point. So that is also interesting. I think the way that you have been, have been introduced to Paul Erdős. By the way, he's like, essentially probably the most well-known combinatorics person. Like graph theory, I will say. And he has, I think, the most number of papers in combinatorics. I don't know, even computer science probably. Nowadays computer science I cannot say because there are all these conferences that the people can publish a lot. But after this conference, like Nurib's and others were there, I think he definitely had the most number of papers. And this Erdős number is like a very famous things that the people. He has done, I think, great work on probabilistic and analysis, especially. I think that's probably one of the main things, and combinatorics, of course. So we just mentioned, but I think the fact that you had access to him, and I think maybe through your mother and the secretary, and talk with him, I think that was very, maybe that actually motivated you more. That might be the case, like, of course, your grandchildren, now they have access to you and you can play even better role. But maybe, it's too easy to access, that may not happen. Yeah, have you tried to talk with them, or they try to talk with you about doing that?
So I tried, with my daughters, I talked a little bit when they were studying in high school, but somehow, and later maybe in university, somehow it was difficult for me. So usually they were not very patient. It's somehow,
I completely know, but I have the same thing with my daughter as well.
Right. Yeah, I don't. And my grandchildren. So there is one who is now 8 years old, one of the eldest, and he's somewhat interested. So he, from time to time, talks with me about questions or mathematical puzzles that he heard in school, and when he's asking, I'm telling him, or maybe sometimes I would tell him some puzzles, but again, not so much. And actually now, anyway, much of the time I'm in Princeton, and he's in Israel, so I see him mostly during the summer or via Zoom. So we don't talk about mathematics too much, but and I don't, as I said, I don't. I'm sure that they will find
their way, essentially.
Right.
Great. And was there anything, like, for example, in high school, especially at that time, for math, or was there anything about computer science actually at the time that you were studying, or not much? Or like, so I think you mentioned 2 programs that you competed on that, but anything other than that?
Yeah, so not much in high school. Definitely when I was doing my first degree at the Technion, so I studied mathematics, but I already took some courses in computer science. And in high school, we also had some excellent mathematics teacher at the end of high school, someone who came from the former Soviet Union, where he was actually training some children to math competitions in Russia, and he had so he was teaching some of us some advanced mathematics, and I was very enthusiastic about that. And then later, so I did my first degree was at the Technion, and the second, because actually one of these math competitions that I won, the first prize was a tuition for all the degree in the Technion. So there I already took also some courses in computer science. And one of the professors of discrete mathematics at the Technion, Chaim Hanani, was also some second uncle of me, so some sort of relative, and he was also a friend of Erdős. They have one or two joint papers, and also through him I met Erdős during my bachelor, my undergraduate studies. Afterwards, the second degree. So I was, in Israel, there is this compulsory military service, and I was in what is called academic reserve, which means that you first study, and then your service is some sort of applied research. But since I was drafted right after the Yom Kippur War, so first they canceled this academic reserve, and I spent a year in the tanks, so in Sinai, like a real soldier. I never fought or something, but it was like but then they renewed it, and then I finished the undergraduate degree, and after that I was an officer in some place of applied research, and during that time I did both the master degree and the PhD, which means that I was never kind of a normal graduate student. I was just coming to the university maybe one day a week, and but when you are young, you can do everything. So I would go to a seminar in the. So my second degree I did at in Tel Aviv University, and the PhD in the Hebrew University of Jerusalem, but both of these were during the service, so I was hardly at the university, and I was mostly studying maybe during the night or studying one day a week in daytime, and then staying in the office until night. So still, it somehow worked well, and I finished a PhD together with finishing the service. So this was 83, and then I did a postdoc in MIT. So I was 2 years in Boston.
So you got your PhD with Misha Perles, and I think on extremal problems in combinatorics in 1983. So and I think that is somehow maybe is some kind of umbrella of all of your works. So how was your work with him? And I mean, do you want to say some stories about the way that he advised? And I think I want to come, I mean, like you have 23 students at least, I mean, according to math genealogy. And I mean, you have, I think, at least again, probably more than that, 79 grand academic children. So so I think the way that he advised, I mean, you there, and the way that you are advising your students. So do you want to say a little bit more about that? Yeah.
Actually, by the way, since you mentioned academic grandchildren and so on, I just had now a paper written with one great academic grandchild. So, so like 1, 2, 3, 4 generations.
4 generations.
So
that's great. I think it's actually great. I mean, the real life, it might be hard actually to catch that things, but in academic things, actually, you can actually have an even probably higher depths as well. Yeah.
Yeah. I think at the moment I only have one academic fourth generation descendant, but there is a potential for several others.
Yeah, exactly.
Yeah, they are right. Yeah. So so working with Micha Perles was interesting. So he was he's a guy that is very good. I think you may know also. So other students of him were more or less at that time, or roughly that time, were Nati Lineal and Gil Kalai. So he had several. But he never wrote much, so he didn't like to write, and he really, one thing he taught me was how important it is to write very accurately. So to check everything 10 times, 20 times, and 30 times, that you always will be able to find typos. That it's very important, accurate writing. And he was really a little bit even obsessive about this, in the sense that, he would sometimes get in his mailbox, one of the usual flyers telling you that, I don't know, tomorrow there will be a power break, and he would take this flyer and start to correct the typos there. So he writes.
But I think he was not writing, correct? So he was just reading and making attention.
So he was writing very little. But he was extremely good, and also he was very interested in combinatorial geometry. So he kind of taught me the beauty of the connection between discrete mathematics and combinatorial geometry and convexity theory, and this was right. But indeed, writing with him, we have maybe one joint paper was really very difficult, because he had to go over everything like lots and lots of times until he was happy with the way it was written. It was which was
I think I had experienced exactly this when I had got my master, actually, with my advisor at that time. I think at that time I didn't like it, of course. It was like one of the worst summer for me that I was writing the master thesis. But I think later, actually, I learned a lot from that. So that I learned a lot from those times, because when you put higher standards, I mean, that is, maybe hard at that time, but later it has been passed, just essentially the usefulness still remains, and then you may be more precise in writing.
Yeah, I think it was interesting. So it took me some time to realize, because he would look at, I would usually come with something I have written with a paper and pencil. At that time, we still didn't type. And then he would look at a sentence for, I don't know, 10 whole minutes, and suggest, I don't know, to move a comma from here to there. But then at the same time, he would also look at the sentence for 10 minutes and suggest to improve the statement of the theorem considerably. So it took me some time to realize that really he's actually very deep, but he wants everything to look perfect. But at the same time, he is also able to come with some great ideas and some. So it was really a good experience, I think.
And have you, published a lot during that time?
So I wrote quite a few papers during PhD. I don't remember, maybe nowadays people write even more, but probably I had 10 or 12 papers written as a student, maybe even a bit more. So I was always interested in kind of a lot of problems, and indeed mostly, as you said, the extremal problems, so problems where we kind of try to understand the maximum or minimum possible size of structures that satisfies certain properties, and this naturally appears in many areas, not only in discrete mathematics, but also in geometry, in probability, number theory, and of course in computer science. So I really like this, and I still like problems in which the word minimum or maximum appears, but you see that it's really everywhere, right? You can say that the PNP problem is the same, right? Because it asks what is the minimum amount of time in which you can solve say the click problem or any NP-hard problem.
Yeah, or essentially any optimization, of course, the minimization and maximization.
That's
and
right.
Nowadays, all the tech, essentially, they try to minimize, I don't know, maybe the delay, they try to maximize revenue. So everything is like that. And I think I will say even the algorithms that is like that. So even when I think that was interesting that when I was talking about my thesis, I said, my thesis was essentially all algorithms. However, there were lots of theorems that I proved about the graphs, like planar graph or Riemann-Free graphs. And but of course, I was using all of these structures to get the algorithm. So in some sense, an algorithm is somehow built of this kind of structural results. And these are like this is the better understanding of essentially this structure that can be, of course, very complicated. As you know, much better in that sense. Great. So now, what about your PhD students? What was the style working with them? Did it change? Because I think I was talking with some other people and said, it was at the beginning is like that, at the end changed to this. So what was the beginning, what was the end, and how was the process?
Okay, so I tried always, and I still try to encourage PhD students to also come with their own problems, to be independent, and actually it's great when they work with each other. Sometimes it happened to me, and I think so most of my students, now I have a few in Princeton, but most of them are from Israel, from Tel Aviv University. And in Israel, maybe it's less common that students collaborate with each other. Like in the US, it's very common. So usually it's and I think it's great when it works. But I also try to think together with the students on problems, and I think it did change a little bit, at least over the years. So one thing is that maybe I became more modest. So when I was young, I was kind of sure that after a few minutes or half an hour that I talk with someone, say a student, I know how talented they are. I kind of can estimate. And it took me some years to realize that this is completely wrong, that what you see quickly is how fast people are, which is an important thing, but some people are extremely deep, although maybe they are not as fast, and then it takes, and in general, different people are different. So there are many ways of being a very good scientist, and I think that over the years I was lucky to have several superb students, and I still am, and I think I actually learned a lot from my students, and I still feel that I'm learning from them, and not only from students, also from other collaborators. And I try at the beginning to suggest some problems and to think together with them. But it's great when they are independent enough to come with their own problems, and this often happens, and it's very nice. So, and I had students both in computer science and in mathematics, and many of them are in have now faculty positions in some in Israel, but also in other in NYU, in ETH, in some other places, and it's really great to see how they develop, and as we said, it's great to see afterwards academic grandchildren, great-grandchildren, and great.
I can continue, I think, hopefully. I mean,
So yeah.
So, one question. So, for example, I think that is like for my students, actually, they all have my cell phone and they are, I mean, we talk, as I mentioned, sometimes we are talk at the middle of, I don't call them after 9 p.m. But if they are, I will send an email, so there's a conference, call me if you are awake, and we may talk actually after midnight even. So, but what do you, so are you having this regular meeting, I mean, with the students, or some of them, they have your cell phone and you are even extended hours, you will work with them? And
so I think, I mean, they have my cell phone, but we communicate more by emails and by phone. So phone is only if, and we try to meet once every week or every 2 weeks, even if nothing is going on, but just to kind of hear what's. But of course, when there is a project that is already developing, then often we meet more. So as we. And then, you know, sometimes we go to lunch here together, or and of course we meet in the seminars here. But I try to meet once, at least once every 2 weeks, even if
not much progress.
Nothing is going on, right?
Great. And yeah, so that so are you meeting them on Zoom? I think you like personal meeting this time.
Yeah, I prefer personal meetings, but of course now because of COVID, and also because sometimes I travel and I spend some time away, then we meet in Zoom also. But I think that one thing that changed with COVID is that we all do more by Zoom, right?
Yeah, exactly. I think learn to do it. Like, and I think that is actually interesting. We will call Zoom, but I mean, of course, there is a Google Meet and Teams and other, but none of them actually become so good as Zoom, especially because I think they were much better, head of Zoom. But like some of the things that Zoom prepared, like this thing that you give a link and this person just click the link and works. Like, for example, with Microsoft Teams, it's not at all like it. You need to log in into your things if you get it your mobile or your cell phone, essentially. And some of the things that they had, it like I think we discussed that we can draw something on when you're presenting something. These are something that Zoom really actually helped in that sense. Like, you should give the credit for that thing. Right. And it's much easier.
Yeah, but still, I definitely prefer to meet in person, when we can. Right.
For the students. Yeah. So I think one of the interesting thing that we had one question also on that one is that like how many hours per day you are working. So just before answering that, I just want to give one other example of that. I think it was like, I don't know, a few years ago, I sent some people to get some letters from them, and it was interesting. So for the others, I sent an email to Noga, and then like one day I didn't get the answer, so maybe he didn't get the email. The next day, actually, I expected that maybe say, okay, I will write the letter or this one, it will come. And then the day after, he actually sent me the actual letter. So that was the speed of the thing that he was working. And I think this is something, I don't know how, these are some people actually I was talking that know you, and they mentioned that, while we are reading a paper, Noga is actually doing a paper. It's not essentially doing it. But I think that is I just want to say, some sort of the way, but I think it is important, like the people, no, this is even for higher schools or others, essentially, or like PhD students. So how much did you work when you were PhD students? now or like in the middle? So how many hours or something like this? If you want, you can share that.
Yeah, so it's, I mean, I like these legends that sometimes are not completely accurate. But
yeah, sure. I mean, that is, I think, as I mentioned, a nice story.
Yeah. But I work indeed a lot. So so I always did, and also now. So assuming that everything counts as work, right? Answering email and thinking. Yeah. So maybe even now, at least 10 hours a day, and probably also some hours during the weekend. And in fact, as you know about us, so even when we are not working, we are actually working, right? Because when
exactly.
we are walking somewhere, we are also thinking. And
yeah, that's the thing that I mentioned. So several great theorems that I have proved actually there were one that I was sleeping at night. In the morning, I came with some idea that idea essentially eventually turned out into actually for my PhD that happened for one of the most complicated one. Actually, it was exactly like that. And in some sense, I will mention to PhD students that if you don't sleep with the problem, you may not be able to solve important problem. Maybe yeah, some smaller problem you can solve, but you really want to solve the problem, you really need to sleep that one in your mind, and your mind should work essentially during the night.
Yeah, I agree, it happens. And you know, and sometimes it's important to kind of change the state of mind, because if you are thinking about the problem for a long time, unless you think about it in kind of different scenarios, different environments, you will keep having the same idea again and again, and you already checked that it doesn't work. So sometimes it's important indeed to go to somewhere else or to think about it just before you go to sleep, and to have some different environment, and this will sometimes help you to get more ideas. It's also helpful to discuss it with other people, or maybe to read some things that is relevant. But indeed, I think that in some sense we are kind of working a lot of hours always, right?
Yeah, that's like one of the things, like, you know, it'd be good or bad, I mean, to be scientists, because like for me, essentially, like weekend also doesn't mean that much, unfortunately.
Sure.
Because I have children that I need to take care of them, but I think thanks to my wife, she's taking some of the burden of that. I have, more time for doing this. And one other question, I think that might be also useful for others. So how do you do the trade-off between emails and administrative stuff versus thinking and writing? Because these are exactly two things that they are exactly against each other and kill each other. I think it's both ways, actually. Yeah.
Yeah, I don't think I'm very good in this. I mean, it's because usually I just get nervous when there are lots of email messages waiting, and I know that I didn't do anything about it. So I feel, so I definitely spend too much time in email, and I never manage to convince myself to, maybe some people do it, you know, to read email only twice a day or 3 times a day or something. I just keep doing it, and sometimes it's not so good. So you definitely need some time to just think. So to live and the same with administration. I mean, the trouble is that administrative duties usually have deadlines. So you have to do them, whereas to think about a problem, you know, at least theoretically, it can always wait. And the danger is that you will find yourself only writing letters and doing committee work and whatever. So you somehow have to force yourself to take some time off, even when you have all these urgent administrative duties, and I don't have a very good answer for that. So, I was many years ago, maybe in 2000, I was for about 2 years, I was a chairman in Tel Aviv. That was still, at that time, mathematics and computer science were together. In fact, one of my main duties was to separate the School of Mathematics from the School of Computer Science at that time. But anyway, so then what I tried, I had the chairman office and I had my usual office. And I tried to spend the morning in the chairman office doing administrative things, and then to go upstairs to my own office and to work on research. And then I found out that I spent more and more time in the chairman office and less in my own, because there were these things that you kind of must do. So I always tried my best, but I don't have a very good method of how do you really force yourself to split the time in an ideal way between administration and kind of research. And but we all do what we can. I mean,
yes. Actually, I mean, we have, added this thing, I think, for PhD advising or like administrative. I think these are, or the way that I think you work. I think that would be useful because I think we have some statistics also, from the, people who are well known in the field and work hard. So what should be the correct thing, like for PhD students or like assistant professor, etc.? I think these are good questions, and I don't have, the answer for them, because for me also, I try to answer the things with some other professor. Actually, something like 3 a.m. we are sending emails back and forth, and this is like, and I feel that this email that I need to answer. I feel bad if I don't answer it. I may forget it forever. So I try to answer it, but generally, that's, as you mentioned, it's a stress essentially in my mind that, okay, I need to answer these things, otherwise it can take forever to answer, or I may forget actually to send a particular email which is important to send. Great. So good. So if there's, anything else you want to say about your graduate students or PhD studies, that's, you can just mention, or then we can go actually to do more research stuff and talk a little bit about the research stuff.
We can. We can speak about research. Maybe there is one funny story that I wanted to tell. It's not as a graduate student, but as a young assistant professor, maybe. So something. It's just a strange story. I don't know if there is any moral to it, but I think it's nice. So let me tell it. So I was already at that time. It was after my postdoc. I was back in Tel Aviv, and I was running to some colloquium lecture. I think maybe it was a computer science colloquium. I don't remember. And on the way in the corridor, I met Amos Fiat. So he's also a known computer scientist, and he just got a book of open problems in number theory, a book by Richard Guy. I think he got it from Adi Shamir, who was his advisor. I think that he just, but anyway, so he just showed me this book. I said that, so it's a book of open problems. I said that I'm in a hurry, let's just open it. I opened it. I tried to look for a problem that would be easy to read, so short problem. And I saw there's some problem of Erdős and Purdy. It's in combinatorial geometry. And I went to this lecture of the colloquium. And during the lecture, I thought about it. And more or less, sometimes it happens, I kind of had the right idea. And basically, I knew to solve it by the end of the lecture. I mean, it took a few weeks afterwards to kind of check all details. Yeah. Basically, it was, and I have a paper. It appeared in this geometric and function analysis in some, but then I showed it to Amos, and I told him, let me take the book and look at it, because this shows that a random problem I can solve immediately. So probably I'll be able to solve half the problems of the book, right? Yeah. So I looked at the book. I went over the problems one by one and kind of thinking about all of them. I had no idea about any of the problems. So somehow, miraculously, the first one that I looked at was the one I could do, and I had no idea about any other thing. So as I said, I don't know if there is any moral here, but it's a true story, and it's kind of interesting. I still don't have a good explanation of what exactly happened.
Yeah, I think when essentially, I mean, I think that is exactly the point about having a paper is not just, I mean, you may work hard on a problem, but you don't have a paper essentially, especially it's an important problem. You need to have the right idea at the right time, and you see the right problem. Like I think they say, maybe having the right problem is 50% of the whole thing, because in some sense, by definition, I mean, right problem is the one that you can solve it. Otherwise, you cannot solve it. That's like the. But yeah, great. So great. So I think let's go. I think I want to start with this work about a streaming algorithm that you actually got this ACM Paris kind of like his award, and that is essentially for the papers that have theory papers that have practical implications, as well as I think the Gödel Prize in 2005. So and they just start by saying a little bit about streaming algorithms. I think from also some of the things that I have seen in the industry. So in general, like this is one of the most two important areas of big data processing nowadays. There is one, it is like parallel algorithm nowadays, is known more as the MapReduce, I mean, Spark and other. These are some of the things that if you even go interview, I mean, the different companies, they will ask questions about it. So it is so things. And this is like, we will call it also massive parallel computation model that you are doing in this parallel computers. The other one is the streaming algorithm that you have lots of big data. You can think about blockchain or other things that you get the data all over the time. And then the question is that when these problems come all over the time, and like the data is coming all over the time, and you don't have a space actually to save everything, or even if you have a space, you don't have time to process that because it would be very, I mean, expensive in terms of compute cost. And the question is that when this data essentially fly in and they are just fly out in some sense, from this you want to compute some sketch and get some statistics, or I mean, some solutions. I mean, is more than a statistics actually. Solve the problem that if the whole graph is given to you, that was the solution. Now you get something. Okay, you may lose a little bit in terms of approximation factor, etc., but still you have a good solution. One particular thing of interest are routers, for example. Lots of routers, when I was actually at AT&T, that was the case, that this router, they needed to compute some statistics and others, and they don't have generally that much memory. So they need to have a very simple algorithms, I will say. And that's also something that makes this model, it is called streaming algorithms, very nice and interesting, because you need to really have simple algorithm to do with that. And this is not a trivial thing to do, because always designing nice, I mean, efficient algorithms which are simple is not that easy. Great. So with this introduction, I want to say actually one of the, this paper that I have mentioned, that's one of the papers of Noga's that introduced this one with UC Matthias and Mario Sedecki. And here, I mean, that's, he got actually this award. So you want to, I mean, talk a little bit about the algorithms there, the model, etc. How did you come to this one? What was the motivation before that? And then we can go after.
Good. Yeah, let me just say that indeed the initial paper was with Yossi Matthias and Mario Segedi when we met in Bell Labs. But then there are follow-up works also with Phil Gibbons from CMU, and the Gödel Prize was with Matthias and Segedi, and the Kanellakis was together with Gibbons also. So that was about. Now, as you described correctly, the main question is what kind of statistical properties you can compute or estimate about a huge stream of data that you get on the fly under space constraints. So you don't have too much space, and you don't want to spend too much time. So you get this stream of data, it comes and goes. You just want to do some simple things for any data item, and afterwards you want to know some property of it, and the question is what things you can compute and what not. Now there were some things also before our paper. Maybe the first one was by Morris. So he knew that you can do approximate counting, and for approximate counting, log n bits are enough to count approximately numbers up to n instead of log n bits. But this is really interesting.
So, sorry, just interrupt you. So, can you maybe define that counting one in maybe a simpler word such that, I mean, that people can get some idea
so
about
approximate
it?
counting means, let's say, that I get items coming one by one, and I only want to count how many of them arrived. So whenever I keep somehow a counter, and then whenever another item arrives, then I want to add one. And of course, if I have log n bits, I can just count.
Yeah, exactly.
And this is fine. But he showed, and what he showed is that if you only want to count probabilistically, and this was already in the late 70s, I think, if you only want to count probabilistically and to have with high probability a good estimate of the number of items that came, then it's enough to have log n bits. And there is a very simple algorithm. But you see, the thing about that is that it's obviously only a theoretical result, because in practice, who cares between, I mean, log n is very small. Even if I don't know, you get all the atoms of the universe as items that come, then maybe the log of it will be several hundreds. So there is no problem to have some several hundreds, and therefore to change log to log is not, I mean, it's interesting theoretically, but it's not, but maybe it's more interesting to try to look at more complicated properties of a stream that is coming on the fly, and to check what you can compute. And we were thinking specifically about frequency moments, but maybe one good way to explain it, suppose you get this stream of data that is coming, and we can think about it that you just get numbers that are coming one after the other. Every number is a big number. Maybe it can be an IP address of something in the internet. So maybe it's a number of, I don't know, 40, 50 bits. And they come and they go, and there are many of them. And suppose you want to estimate, for example, you want to know if some number appeared twice. Is it true that all of them are distinct, or someone appeared twice? Or suppose you want to approximate the number of pairs that appeared that are equal to each other. Or, okay, so things like that. And we thought that it's an interesting model. I think that at that time, so this was in the late 90s, it was still not clear how practical. So, you know, the big data only just started. We didn't know that there will be such huge amounts of data that you would have to process, but still it looked interesting. And surprisingly, what we realized is that there are some things that you can compute with very little space, and some things that you cannot. And in the examples that I said, if, for example, you want to know if there is some numbers that appeared twice, then you can show that you cannot do much better than just to remember everything. I mean, of course, you can store a table of all the numbers that appeared, maybe as a hash table, but still you would need lots and lots of memory. And then whenever someone else is coming, you check if it appeared before or not. But this requires a lot of memory. And it turns out that using some known results in communication complexity, you can show that you cannot do much better. Now, we also realize that in general, for basically any interesting task, you will not be able to compute things exactly, but you have to have some approximation. And also, you will not be able to do things deterministically. You need to have randomized algorithms, so you need to just be okay with high probability. But then the surprise was, so we found some basically pretty simple, but not trivial, maybe, algorithm that will count the second frequency moment. So basically, it will approximate how many pairs of items, of numbers appear that are equal to each other. So for this, you have to do something randomly, and we use some random projection and maybe four-wise independent random variables. So I'm just saying the relevant buzzwords, and it turned out that this you could show that with a amount of memory that is only logarithmic in the amount of data or the range of the numbers that appear, you are able with high probability to get a good estimate of the number of pairs of items that are equal to each other. On the other hand, for some things that look pretty similar, so suppose you want to estimate how many, I don't know, 4 tuples of numbers there are that are equal to each other. I want to know, so this would correspond to the fourth frequency moment. Then this you cannot do in logarithmic space. You need space that already grows like a power of the range of the numbers that can appear. So some things that look pretty similar to each other, some are possible under space constraints, and some are impossible. And this was quite surprising for us. And it used, so like the positive results used some sort of randomized projections, and it's related to some geometric ideas. And the negative or the lower bound results used ideas from communication complexity. And both of those turned out to be very influential in the sense that soon after that, really this area of streaming algorithms became an active area, and with lots of ideas by many clever people that were extending what we did and generalizing and doing some other things, both for upper bounds with clever algorithms and for lower bounds with techniques mostly from communication complexity. And the nice thing that kind of the basic approaches, I think, appeared in what we did already at the beginning. So both these randomized projections and the connection to communication complexity. And the fact that it later turned out to be really practical. So you can monitor traffic in internet. You can even at that time. So as I said, I was visiting Bell Labs, and maybe both Yossi Matias and Mario Segedi were actually working in Bell Labs at that time. So we made a patent of this basic thing, and it was implemented in some software that supposedly was used by Walmart. I never checked how practical this original thing was, but I think in general definitely the area became practical. And it's always nice, I mean, although I view myself as a theoretician, but but it's always nice when it kind of turns out that that something that you've done is really useful, and it's and this was the case with this thing, and I think it really became an active area. So we also, from time to time, I'm still working on streaming, but definitely there are lots of many clever and younger people who were doing and are still doing some great things about this area, where the main thing is that, as you described at the beginning, what kind of properties you can compute or approximate efficiently under space constraints on the fly. And it's still not completely clear what is the situation with, I mean, sometimes there are several tasks that look very similar to each other, and one of them you can solve efficiently with very little space, and the other you can show that it's possible. And it will be interesting to understand better what are the things that can be done and what are the things that cannot.
Great, I think great explanation. So I just want to add a few things, especially because I'm working on both these models of big graphs or big data, things about MapReduce and streaming algorithms. So I think a few things that I think that you mentioned, I just want to say summary on that thing. So in some sense, like the idea generally, I think we want to have ideas that there is some data of size n is coming, say, of course, I mean, so the memory that we generally would like for this type of things, I mean, to have memory of log n, because like somehow exponentially smaller than that. Of course, we can go, as Noga mentioned, from log n to log n for some problems, but maybe actually going from, and it is also exponentially down, but maybe from n to log n is the most important problem. I think this paper that Noga had about like several problems, like he mentioned, like finding like heavy hitters, like the person who is coming the most, or several other versions of metrics or norms, etc., that we can compute it. Another interesting one actually about the graph problem. So that also the people consider it under the name semi-streaming. The semi-streaming is that a graph typically can have a dense graph, can have, if n vertices it can have n to the 2 edges. And then the question is that can we do this like from n squared to n, the space that we have? That was the semi-streaming model. And by the way, when we talk n, we may have n log n and n polylog. As I mentioned, polylog is the acceptable things that we can have. I think we had actually this problem. I think probably we were the first actually. We could get for one non-trivial problem, we could solve find the degree of vertices or something less than things. But for example, for matching in planar graphs or somehow a sparse graph, actually we could get something sublinear. That was, and I think later had been improved actually to log n, and there are several works there. So these are very nice problems, and I worked actually with a master student at that time. For several trivial problems, you couldn't do anything better than n. But then when you try to approximate something in this graph, and actually you could do better. So there are very nice set of problems here. And also I want to add one thing about the practicality. I mean, how practical is that? So this was some story. I mean, like the past few years, I'm doing it more. Also, I mean, from the, I would say, technical stuff, and I mean, maybe more system things as well. I actually loved it, because if you have the theory and you will go there sometime, I mean, we need some other people to say what are the applications. But if you go and understand the application, actually, and I think it needs a little bit of hacking, programming, etc. as well. But actually, you may enjoy, because this idea that you had, now you can actually do it better than practitioner. So one that I was reading actually recently, that was Google. Actually, they had this thing, they will call it, I mean, very secure system, and they sell it to different companies. It happens that I think this is exactly the application of the problem that you mentioned, that for one company, it was like that. Some hackers, they want to hack it. The way that they try to do that is that using different IPs, I think like 5,000 IPs or something, and sending requests from different places to this website. And that is interesting. If you allow that this traffic comes inside, then it essentially crashes your system. And if it is in Google Cloud, it may actually have effect on the Google as well. The issue is exactly the one that you mentioned. You want to have very, so like you want to have routers or very resource restricted things at the edge, such that they will find this type of attacks and probably report it. Or the one way actually that they were doing very nicely is that this was for this particular company, they were sending, I don't know, the amount of traffic that you will get in a big company in 1 week in I will say in less than an hour. And it was horrible, but the way that they done it was very nice because they could first understood it very well with a very restricted memory that this is a bad type of data. They report it, and this is the typical thing that they are doing. I think they are throttling it. Throttling it means randomizing drop, and essentially randomly drop it. So they randomly drop this one. Even these guys didn't, some of their things still went through. And they have for 1 hour, having such an attack generally is very costly. They say, oh, nothing happened, essentially, only their things became slow and they went away. But you see, these are nice theory work that when you put it in the right place, can actually catch such things because of this efficient algorithm. And that's actually beauty of this. That
yeah. So this is against the denial of service attacks. So some particular right. Yeah. So indeed, I think it's nice when theory work turned out to be practical. You can if there are like great examples like RSA crypto system or LAMP-LZIV compression schemes. So these things, if they wouldn't have the application, they would be kind of nice, but just nice. But once they have this application, they are really great. They are really changing the world. So that's why I'm mentioning RSA and LAMP-LZIV, which are really things that are very influential in practical applications, and streaming is also practical. Probably its impact is not like one of these two things, but it's still significant.
Yeah, and I think one other thing I wanted to tell about Noga in that sense actually. But when I talk with him and work with him, and when you mention a nice problem, I think he appreciates the problem, and I think that is important. Maybe some people say, "Oh, this problem is not. It's my area, or maybe it's just not. I don't know what would be the prospect of that, whether it gets in the top conference or not. I think at some point actually it might be better to just think about these problems if you can solve them, because you never know which one of this work actually may come essentially the very practical one. And I think that's important to me. I think that's the style that I looked at. Well, do you want to add anything on that?
Yeah, no, I agree. That's very important. So I think to maintain curiosity is very important. And indeed, it is true that often we don't know to begin with when we hear a problem. It's hard to estimate if it will be important, whatever that means, or not. And important does not necessarily mean practical applications, but for example, maybe it will lead to some new important insight. It will lead to a development of an area so I think it's indeed very desirable to kind of look at problems and stay curious about them and give them a chance, even when it's not. Sometimes at the first look, they may look a little bit artificial, but it turns out that this is not the case. And actually, it's something that you often, that Erdős used to ask lots and lots of questions, mainly in combinatorics, but also in number theory, in some. from time to time you would hear from him, and he had a very good intuition of what problems are interesting. And from time to time it happened to me, and I know that several other people told me that they had the same impression, that you would hear a problem from him and you would tell yourself that this is really not interesting. I mean, it looks, and more often, and of course, maybe sometimes it was not, but more often than not, it turned out that really, after you think about it, it turned out to be somehow the right problem. So although it looked a little bit artificial, it led to something else. It was a special case of something. It was, and this is the case with many questions. So I think it's nice to stay curious and to give problems a chance. And I think this is more or less what you said.
Great. Yeah. So actually, by the way, so I just mentioned that we are live, we are global, we are on every medium almost, I mean, like YouTube, Instagram, Twitter, LinkedIn, and Facebook. Some of the questions that some of you asked in different, I mean, especially LinkedIn, Twitter, and Instagram, these are the best way to ask questions. I mean, you can ask, some of them you asked already answered, but I mean, or ask Noga some of them, but please ask more questions as well. Great. So I think we will talk about the next thing. So we talk about the big data, we talk about the streaming, and I mentioned there's another one about the parallel algorithms. And that's the way essentially we are getting the big data. So in some sense, in the streaming, we have one data, one computer, your own laptop, actually, we even motivated, and you want to solve some problem. You may read from the hard disk. That's another kind of a streaming algorithm, or your cell phone. The other way is that, of course, we are using cloud and we have parallel algorithms. And I think we come to this other paper that you had about the fast and simple randomized algorithm for maximal independence set problem. I think the maximal independence set problem is that you have a graph, a set of nodes and vertices, a very important problem. You find maximum number of vertices that they don't have any edges in between. Or you can consider the complements. You want to find a set of vertices that they have all edges in between. So these are clique versus independence. And now you want to find a maximal version. So here you don't want to find the maximum one. You just want to find one that you cannot add one more edge to it. It seems actually easier. It's the polynomial time problem to find the maximal one. But here we talk about parallel algorithms, and you want to do it faster. So you don't want to do it, say, linear in n again. You want to do polylogarithmic or something faster. So yeah, so I think this work of Noga with Lassi Babai and Alon Itai actually got a Dijkstra prize. So you may want to talk a little bit about this.
Yeah, so let's also say that my Klubi independently came with essentially the same result, and indeed we got. So the problem is indeed what you mentioned, and the thing was to find a parallel algorithm that solves the problem in a logarithmic number of rounds. And it turned out that there was a relatively simple and elegant algorithm. And let me also mention that in the same paper, it kind of led us, because the original algorithm was randomized, but then we wanted to de-randomize it, to convert it to a deterministic algorithm. And for that, you had to use the notion of small sample spaces supporting k-wise independent random variables. So small sample spaces in which we have random variables so that every 2 or every 4 of them are independent. And that also turned out to be something that is useful for other algorithms. But I want to mention another thing that is related to this paper. So this came as a follow-up result that we wrote much later, maybe sometime in 2010, maybe, with a group that work also in biology and also in distributed computing. And this is a paper that appeared in Science, and it's again, so it's the following. So the motivation there came from something that happens in the development of the nervous system of the fruit fly. And apparently, when this happens, then some cells have to decide if they want to take some special role or if they just want to be simple. I mean, I'm kind of simplifying it, and actually because I'm not even very familiar with the exact biological details, but it turned out that basically what had to be solved there by the nervous system is to find a maximal independent set in some graph, because these are these cells that choose to have this special role. And somehow our impression was, and the kind of the biological experiment supported, is that these cells during the development, they can do only very, very simple things. They cannot count, they cannot, like even our algorithm in that paper with Babai and Itai, it was simple, but still it was counting degrees of vertices and was doing some things based on the degrees. And here the assumption was that the biological network does not even know to count. So we considered only an algorithm that would solve this maximal independent set in parallel quickly, but is allowed only to do very, very simple things. So maybe it's allowed to use randomization, and it's allowed to only, we call it beep. So it's only allowed to send or not send one bit to the neighbors every time. So it looks that with this, you cannot do much, but because we had the results from the older papers and the algorithm was simple enough, then it was possible to indeed modify it and get an algorithm that maybe not in log time, but in log square time, finds with high probability a maximal independent set, and it does only very, very simple basic operations. And somehow there were reasons to think that what the actual biology does, what actually is actually happening, is very similar to this simple algorithm. So I think that this, and as I said, there is this science paper that describes it. And I think that one nice thing about this paper is that it kind of tells you that sometimes just by thinking about biological systems, about what they can do only very simple things, then you will be able to find some new algorithms to interesting problems because you are restricted by the kind of operations that the biology enables you to do. So there are also people that work on what they call the natural algorithms. So they try to understand how biological systems behave and to kind of understand it mathematically. But I think indeed one thing that is nice about this specific paper, so definitely it was motivated by the thing in the original paper about this maximal independent set, but it made it even simpler, allowing it only to use some very, very basic operations, and this has some advantages and maybe also explains what is happening really in this biological system.
Great. Yeah. So I think to just mention maybe the algorithm. So here, let me ask actually first this question. So Lubis algorithm. So was it? I think that was log n versus log n to the 2. I mean, how do you compare your result with Lubis algorithm?
No, I think both of them were log n. Basically, the number of steps, the time was logarithmic. And then maybe in parallel algorithms, you care also about the number of processors. And so they were very similar. And basically, the basic approach was that everybody looks at its degree
Yes.
and chooses itself to the independent set with a probability that is proportional to 1 over the degree. And then if we have some collision, so some two adjacent vertices decide to choose themselves, then they both go out of the independent set. And this is like one round. And after this round, you take these resulting vertices to the independent set that you are constructing. You remove all their neighbors and you keep going. And the trick is to do some analysis. Now it's described as a randomized algorithm, and to show that in expectation, the total size of the graph decreases by a constant factor in every step, and therefore you will finish after a logarithmic number of steps. And then there is this issue of making it deterministically, a deterministic algorithm, because you only need the random choices to be pairwise independent, because somehow what happens for a vertex and some, I mean, because edges is only two ends, so you care only about pairwise independence, and you can use these small sample spaces with supporting on this.
Great. Actually, I want to just mention that I mentioned the algorithm that you already mentioned. I think that you mentioned just a summary, essentially. You want to find a set of vertices that no one has an edge, and at the same time, between each other, and we cannot add one more vertex. This maximality is the important things, actually, that it is important here and make it nice. So the thing is that, I mean, each vertex, as Noga mentioned, I mean, according to some 1 over degree, decide to be in the independent set. If there is a collision, both of these guys go out. We have some independent set, and the current thing is the independent set, but it's not maximal. I think that's the catch. And then the issue that, okay, these guys, we will select it in your solution and say, okay, remove their neighbors, because the neighbors cannot be in the independent set. Then we need to repeat this process. And we need, I think the interesting thing would be here to repeat and say, how many rounds do you need such that you can actually have a maximal independence set? Because until you are not done with the graph, you don't have a maximal independence set. Still, you might be able to have one more vertex and you be maximal independence set. So that number of rounds would be important. Actually, we were doing, I mean, similar thing for the matching when you consider essentially maximal matching. We had it recently. I mean, that was I think a few 2-3 years ago. That was we are doing in parallel. That's also this maximality. Actually, these are important things and can be actually complicated algorithm. We do it log n, but in these massive parallel models. And I think for your case, I think that would be a log n in this like. Maybe there's a little bit different between the regular parallel and the massively parallel model, because there we have computers that they have more power essentially.
Okay.
Great. So I think now it was maybe the good things also to, you mentioned about this one interesting thing about this, that this, and the one beauty of this algorithm is that each one decides globally to be in an independent set, which is a global solution, by just seeing essentially its local neighbors and decide whether he wants to be there or not. And I think this is also some important, this kind of local algorithms are important algorithm in property testing. That's another thing that you are actually working. So you may want to add a little bit more on that things that now we are here.
Right, yeah. So it's indeed very interesting to decide. So for algorithms, these are local algorithms where everybody has to decide what to do based only on its local neighborhood, and still you want to get some global structure. And in property testing, it's you want maybe to understand some global property of a structure that can be a big graph, for example, by looking locally at a very small part of it. And you want to understand what properties you can deduce by looking at only a very small part, and what properties you cannot. And it's quite surprising that there are quite a few things that that you can deduce about the global nature of a graph by looking at a very small part of it chosen randomly. So, so this was in the graph model. It was initiated by Goldreich, Goldwasser, and Ron, and maybe before it in general by Sudan and Rubinfeld, and it turned out to be closely related to some very basic result in graph theory, which is called Semeredy's regularity lemma, which tells us something about the structure of a general graph, and using this type of connection, it was possible to kind of characterize all the properties of graphs that can be what is called tested in the dense graph model. Now, to formulate everything here exactly, we have to define what exactly we mean. So there is one notion that is needed is the distance between a graph and a property. And we say that the graph is epsilon far from satisfying some property if we have to change an epsilon fraction of the description of the graph in order to get a graph satisfying the property. And the objective in property testing is to distinguish between graphs that are epsilon far from satisfying a property and graphs that satisfy the property. Because since you allow yourself only to look at a very small local part of the graph, you will not be able to see if the graph does not satisfy the property only because of some small number of edges somewhere, right? Because we are not looking at all of it. But surprisingly, it turned out that that in fact every hereditary property, so there is a huge number of properties of graphs, almost every natural property,
which is hereditary,
that you can distinguish between a graph that satisfies it and a graph that is somewhat far from satisfying it. You have to delete or you have to change an epsilon fraction of the representation in order to get something that satisfies it by looking at a kind of a constant part of the graph, a constant that depends only on this proximity parameter epsilon. So, so maybe just to give a specific example, suppose I give you this huge graph, so a large graph, and the only allowed operation we're allowed to do is to query if vertex number 1,000,002 is connected or not connected to vertex number 10,000,000. And we can ask some queries like that. And what we want at the end is to know if, with high probability, let's say, to distinguish between the case that the graph is 3 colorable, namely, we can color the vertices by 3 colors with no 2 ends of the same edge of the same color, or the alternative is that we have to delete at least n square over 1,000,000 edges to make the graph 3 colorable. Okay, so these are, and the surprising thing is that this can be done by an algorithm that makes only a constant number of queries, independent of the size of the graph. So the constant will depend on these parameters, 1 over 1,000,000 that I mentioned, and this is, although the property of being 3 colorable is NP-hard. So in fact, we had in one of the papers we had later, this was about some sort of approximation algorithms. So suppose you give me any monotone graph property that you want. So a property is monotone if whenever a graph satisfies a property, then so is every subgraph of it. So for example, being three colorable is monotone because if you delete edges and you are three colorable, you stay three colorable.
Yeah, so if you, I think the three colorable is that, I mean, coloring essentially you want to color the set of vertices such that any two vertices that have an edge have a different color. And the three colorable is that with three color we can do that. And of course, if the whole graph you can do it with three colored, if you delete some of the edges, still you can do it for three colored.
Yeah. So this is an example of a monotone property, but there are really lots and lots of examples of monotone properties. And suppose I give you this a very, very big graph, and your objective is to estimate or to compute the number of edges you have to delete in order to get a graph that satisfies the property. For example, the number of edges you have to delete to make the graph three colorable. In particular, the number of edges you have to delete to make the graph two colorable is equivalent to the so-called max cut problem of the graph, because this is a, and then the result is that if you only want to approximate the minimum number of edges, you have to delete up to an additive error of epsilon n square. Then for every monotone property, no matter how complicated the property it is, you can do it efficiently. You can do it in linear time. And in fact, if you want to do it randomly, you can do it in constant time, only constant depending on this epsilon. And on the other end, if you want to approximate it not up to an additive error of epsilon n square, but up to an additive error of n to the 2 minus epsilon, that's already NP hard. So probably there is no efficient algorithm that does it. But indeed, it tells you that there are lots and lots of things that you can do very efficiently locally, although I should say that the positive results there are completely non-practical because they are based on this thing that is called the regularity lemma.
Yeah,
so the dependence on epsilon is completely terrible, but still for constant epsilon, it's a constant.
Great. So yeah, I think that's actually, I wanted to add something, like as you mentioned, I mean, Noga has like over 600 conference and journal papers, so we cannot go through all of them. But I think as we have seen so far, and I have seen some other works of him, that is actually, that is the beauty of, the way that, he's thinking about that. So we have a graph, like some structure, and generally, even in the streaming algorithm, we cannot see the whole graph. We want to see a little bit of this graph. And of course, if we don't see the whole graph, then we may make a mistake. But you want to say that, okay, our mistake somehow bounded, like in terms of like the probability of mistake is bounded. So for example, I think we were talking about the property testing that you may see actually just a constant number of places in the graph. And of course, randomness plays a very important thing in this probabilistic method. And the proof that why it works, that these are the non-trivial parts. Because the algorithm probably lots of people can say, but why does it work? That's a non-trivial part. But then you want to see a little bit of this and then distinguish, for example, the graph has this property or very far from this property. These are like some kind of property test. And these are very nice set of, work. I think the work of Noga, I forgot the second, I think Asaf Shapiro was yeah. And this was one of the latest one actually that put somehow the most general version of the previous works. I don't know, some other later work came after that, but that was one of the important one actually in the...
right, yeah. So with Asaf, what we showed is that every hereditary property is testable, and then with him and Newman and Fisher, we had this basically characterization of all the things that can be, that have a two-sided tester. But so property testing for the dense model of graphs, we in some sense understand it completely. But in sparse models, there are still some interesting problems that are
great. Yeah, so I think, so having said that, actually, now I wanted to mention about another problem. I think that actually, like this was the paper that I had in this Bobby Kleinberg, Tom Layton, and I think Steve Butler, about a hat guessing game. So this was somehow this is a very, interesting game that the people have different version of that. Like these are like as a maybe a puzzle. And the question is that, there are some people, they cannot see their hats. And you know that there are this number of hats in the, I think this is like make it also a bit less, more like a puzzle version of the thing. Then we will go again to some other research as well. But here you can see from this problem that, okay, there are a set of people, they have a different height, they can see the hat of others. And you know that this number of hats exists in the, essentially in the room. And you cannot see your own hat, say. How can you essentially guess what is the color of your hat? And there are several, versions of puzzles of this that you may heard for two people. For two people, I think I can give you a simple example that there are two people, like person one and person two, and they can just see the hat of the other person, not themselves. And then the question is that we know that there are, it might be essentially two colors at most. These two people, but these are you know that it is green and red. It can be green or red. And the question that you want to see the color of the other person's hat, and then you decide what is the color of your own hat. So it seems maybe at the beginning it's like too hard, but actually this is the interesting thing. So the question here is that we may not get everything exact, but you want to get some approximation to the problem. For example, if there are two persons, two color, red and green, one strategy would be like this, that among these two persons, one of them just say the color of my hat is the same color of the other person. The other one, he said that my color is the reverse of that color. Interestingly, you can consider that whatever the color of these guys, at least one of these guys said the truth correctly. And this you can generalize it more. You can make actually the graph version of that you have a graph and some people can see the other information. This actually, there might be actually some interesting applications for that some people see some applications and they don't, some information of others and some other information that you don't see. And you want to make sure that in the worst case, a good fraction of these people or some number of these people actually make the correct guess. So this is, again, I might be wrong, but in total, we are guessing a good thing. So actually, we introduced the problem. And I think the result that we had, just several of them are not, some initial results. But I think this is one of the things that I see actually Noga worked on this, and he had some of the best numbers that I'm enjoying reading the paper. So you want to say a little bit the state of the art. I think I checked some of the papers, but I don't know what is the current state of the art actually now.
Yeah, so I really like this problem. So indeed, we saw initially this problem in the paper of yours with Steve Butler and Bobby Kleinberg and Tom Layton. Yes. And you had several versions, but the version you mentioned is the version that I really like. And now there are quite a few recent papers about it. So let me just repeat what you said, because I want to look at one particular problem that you mentioned in your paper. So we have this group of people, and now what I want to consider the case of a complete bipartite graph. So let's say that we have boys and we have girls. Okay, so we have boys and girls, and each one has a hat on his or her head, and the color of the hat comes from some k different colors. Okay. Now, in this version, as I said, it's a special case, but an interesting one. Every boy sees only the heads of the girls, and every girl sees only the heads of the boys. And then, based on this, everybody has to guess his or her own, the color of his or her own head.
And we know how many colors total, correct?
Yeah, and we know that they all come from K colors, right? K different colors. And everything is deterministic here, no probability. So really, just my guess as a boy is a function of the colors that I see of the girls that are in front of me. And okay, now the group as a group wins if no matter what colors assignment we give them out of k colors, at least one of them guesses correctly. But we are fine if only one guesses correctly. Okay. So you start thinking about it, and actually what Mohammed just described was a special case of this of one boy and one girl, right? One boy and one girl, if they have heads of two colors, then one of them can guess correctly. So the boy will guess that his color is identical to that of the girl, and the girl will guess that her color is the opposite of the boy's color, and of course one of them will be correct. And it's not difficult to show that with more colors, if they have three colors, they cannot do it. Okay, but now if we have two boys and two girls, then it turns out that even if the number of distinct colors is three, they can still do it. So, so with three, it is, and that's, so again, there is some way for each one to decide about function. Actually, even the functions are linear functions of the colors that you see for each one.
Yeah, these are the can be, I mean, actually, I don't know, math challenges or math Olympiads, etc. These are the for the case of yeah.
Now, what happens for a bigger? I mean, in general, it looks that because the boys only see the colors of the girls, and the girls only see the colors of the boys, it doesn't help them to guess their own, right? So
exactly. That's I think that's the beauty of that. I want to say, like when you dive deep, there is actually some relation from these seemingly unrelated things.
That's right. Yeah. So it looks unrelated, and in fact, the following can be shown if you insist that the guessing functions are linear functions of the colors that you see. So there is a way to describe it as linear functions. You embed it all in a field, but never mind. And as I said, for the small cases, the examples are linear. So if the functions are linear, when the number of colors is already 4, then no matter how many boys and how many girls you have, they will not be able to do it. So there will always be an assignment so that they will all fail because it's a linear function. But on the other hand, what happens if it's general functions? So already in your paper, you show that, that then the number of colors grows to infinity together with the number of boys and girls. So you had some weak estimates that if the number of colors is maybe log n, and we have n boys and n girls, then there is some way that at least one of them will be successful. And this is kind of surprising. And we were looking at this. So we have this paper with Ben Eliezer, Shangguan, and Tamo. And we could show that even if the number of colors is close to square root of n, then when we have n boys and n girls, we can guarantee with nonlinear functions, right? So we can guarantee that one of them will be successful. And it's kind of a nice example where there is this dichotomy between linear and non-linear. Something similar happens in information theory, something called network coding. So it's somehow, but I should say that we still don't understand, and I think this is a nice problem, and this is one of the problems that you suggest in your paper, to understand exactly what happens for this complete bipartite graph for boys and girls. So suppose we had n boys and n girls, and the number of colors is now maybe n over 2, something pretty big. Can we still guarantee that at least one will be correct? We don't know it. So to prove that we can or to prove that we cannot, both directions will be interesting. Okay? Now, there are several versions of these problems and of these head guessing problems, and you can ask it for general graphs, but I think this, and even people found some connection to it, to some questions in communication complexity and in dynamical systems and so on. But I think I agree with you that it's interesting just as a puzzle, and just to understand what is happening for those boys and girls example is already very challenging and very interesting. And indeed, recently there have been quite a few papers on variants of this problem, and it's definitely not, although it's so simple to state, it's not well understood. And I think this is in general one nice thing about discrete mathematics and often about problems that come from computer science, that often problems are very simple to state and are very hard to solve or to prove. And often the proofs use tools from different areas. So here to show that linear schemes cannot work, you have to use some properties of polynomials. So you could say some basic results, but still results from algebraic geometry or properties of roots of polynomials. And although it's a problem that is very simple to state, we don't know the solution, right? So it looks that so it's a challenging thing, and this is what makes it so fascinating.
Yeah, I think this is actually unique to combinatorics and discrete math that I mentioned. So there are other areas of math like algebraic geometry or especially particular. These are the areas that like you want to think about the problem. Probably you need to. I think I had some actually friends at MIT that they need to read maybe 2, 3, 4 years to read the materials to see what is the actual open problem here. But here in combination, like this is the problem that we mentioned. It's like a very simple one. There are n boys, n girls, like n over 2 colors. And the question is that can these people do anything such that they can at least one of them guess the correct has a correct guess of his or her own hat. It's very simple to state, right. But I think to want to solve it, it's like you may need to use lots of techniques and things, and that actually makes it interesting. I mean, somehow to some people maybe say, oh, this is like a simple problem, but at the same time, I mean, to solve it, you really need to do harder stuff. And probably it might be harder than some other algebraic geometry problems that you solve because you are, as you mentioned, I think you are on top of the mountain and you solve some problem. Here in the ground, but still you need lots of techniques to solve the problem. So, and I think in general, this intersection of, I mean, you are doing a lot of this with the intersection of algebraic geometry, topology. And so, like, I think if I'm a PhD student, I want to be, I mean, essentially more mathy stuff. Is there any general advice that when should I look at essentially math? And because this is, I think maybe there are more connection between theoretical computer science and math. For example, the PCP theorems or lots of, or like, for example, as you mentioned, network coding or other stuff. But in general, I think this is the question. Embedding, this is also another place that's lots of intersections. But I mean, when should I look at it and where should I look at it for math things if I'm working in the theoretical computer science? Because that's some question actually some of the people asked me on that.
Right. Yeah. So I think that by now there are several pretty good surveys of people that write about using specific methods in computer science or so there are like books on the polynomial method. So just to use some simple or not so simple results from algebraic geometry to solve questions that are combinatorial in nature. And actually in our first papers that you mentioned about this embedding, we were using this Milnor, Tom, Warren. So those results from real algebraic geometry that give some bounds about the number of sign patterns of polynomials. I mean, in general, polynomial is a very basic notion in mathematics, and it turns out that understanding properties of roots of polynomials is very powerful. And algebraic geometry, basically what it deals with is the properties of roots of varieties, so of just systems of polynomials, and this turns out to be useful. And I guess in books about computational geometry, you will see usually some material that is covered, and also topology, so things like Borsuk-Ulam theorem or fixed point theorems are also often useful for algorithms.
As I mentioned, so I think I will suggest that anyone who wants to do like on probabilistic and random, they really definitely should read your book, The Probabilistic Method with Joel Spencer. I actually use several parts of it, and like about the Talagrant inequality and other the beautiful thing. Are there some books that, I mean, maybe it's easier, not that hard, but it still would be useful for a student in computer science essentially to read it, especially more theory background?
Right. So I think Matuszek has this book about, I forget the exact title, but the applications of Borsuk-Ulam theorem.
Yeah.
So it's like a small, and it basically gives some very nice applications of the basic topological tools to get results in that really often look completely combinatorial. I can mention actually, so that's another paper of mine, early paper of mine that I like. It's called the necklace theorem. So this is, again, it sounds completely discrete, and actually it originally came from a question of Layton and Lizerson. So they had the motivation, this was in the 80s, from VLSI circuit design. Nobody cares about this area anymore, but still it's a very natural question, and but let me tell you the statement. So suppose we have a necklace, and so necklace, I think, and we open it, it's a class, so it is just an interval of beads. Okay, an interval of beads of different kinds. And so we have red beads, and we have green beads, and we have yellow beads, and we have, okay. And suppose we want to split the necklace into K collections. So one way to think about it is that this necklace has been stolen by K thieves together, and they want to split it in a fair way among them. Okay, so so they want that each one of them will get exactly the same number of beads of each type. Let's say that the number of beads of each type is divisible by K. Okay, and what they want to do is they want to cut the necklace. So it's this interval of beads. We want to cut them in not too many places, and then we'll get intervals of beads and split the intervals into K collections, and each collection will contain exactly the same number of beads of each type. Okay, and the question is how many cuts we need.
But you can do that.
So let's see some example. Here is an example of a pretty simple necklace, namely, suppose that all the red beads appear contiguously, and afterwards all the yellow beads appear contiguously, afterwards all the white beads and so on. So just to cut the red beads into K collections, you need K minus 1 cuts inside the red part, and K minus 1 cuts inside the yellow part, and K minus 1 cuts. So altogether, you need K minus 1 times T cuts if T is the number of types of beads in this example. Okay. Now the theorem is that K minus 1 times T cuts are always enough. They always suffice, no matter how complicated the necklace is.
So, what was the bound K minus 1 times?
Times T. T is the number of types, times the number of types of beads.
And so here, by complicated, it might be that we have a few red, then a few green, then a few red again, and so on and so forth.
That's right, yeah. And it can be completely complicated, right? Very, very complicated. And the statement is that always K minus 1 times T cuts are always enough. And the proof of this, so there are several nice things about this thing. So the proof of this is topological. I don't know any non-topological proof. So it uses and the proof, because it uses topology in an essential way, it does not give an algorithm. So we don't know how to do it efficiently. Suppose that K and T are big. So we know that there is a way to find the cuts, but we don't know how to find them. Moreover, it has been proved recently by Goldberg and Aris Philos Ratsikas that the problem of finding these cuts is what is called PPA complete. So it is complete for some complexity class, namely, in general, to find such few cuts is probably difficult. We don't, if we know to solve this, then we know also to find Nash equilibrium. We know to solve efficiently all kinds of problems that we don't know how to do efficiently.
But that's a PPAT complete, correct?
So it is PPA complete, which is
PPA
more than PPAD complete, but it is PPAD hard, right? Because PPAD is contained in PPA. But this is so right, and something similar happens to some of those combinatorial applications or computer science applications of tools from algebraic geometry, that they give results that do not provide efficient algorithms. There we don't know hardness results, but we don't know an algorithm. So I give you
actually, I mean, a very similar thing that we had also some work on that one. It's about the fair division problem of a cake, because there also that is like you have a cake, you want to have a bounded number of the cake. I mean, we had this one actually. I think it was some Fox paper that actually they got it for the fair division. We had this one for the like a chore division. That this is like negatively saying the people want less of that instead of they want more of that. And that's also, I mean, getting that actually generalized the positive version. But these are, I think there might be some relation between these are because the similar type of thing, the cut there, and I think don't remember the exact ones, but I think some of them we can show that there is a bounded number of things. The bond is still horrible. I mean, like the things is not like the best bond that you have it, and I'm not so sure that actually we had the algorithms for that case, even for that bond. So the same type of thing that you mentioned. And is there any upper bound on the problem? I mean, that you can do it algorithmically?
Yes, so we have so first I agree it's very related these cake cutting problems, and indeed this has the origin with Steinhaus and Banach in the 30s. It's really but now for the problem that I mentioned, we have a pretty recent paper with someone who was a student in Princeton. He's now in Stanford, and Andrew Grauer is his name. And we could do a number of cuts that is something like K times T times the logarithm of the length of the necklace. So it has some dependence. There is no known algorithmic version that gives any function of K and T. All the known algorithmic versions, they grow with the length of the necklace.
With the length.
And it's very interesting, I think, to find something better, because the hardness result just says that it's hard to find a very small number. But
so potentially, I mean, it can be like maybe the exponential in K and T. That would be the
So that's right. Even this is not known, and I don't know any function of K and T. Because indeed the only proof that we know uses this fixed point Borsuk type theorem basically, and this is not algorithmic, and it's not clear how to transform it to an algorithm.
Actually, we already mentioned, I think we had some open problem section. There are two things that we mentioned. I think one for this hat guessing game for the graph, bipartite graph, and the number of things is linear. I think the other one is this nice problem that is still I mean, when did you have the first paper on that?
The original first paper is very old. Maybe it's in 86 or something.
86.
In the 80s. I was still in MIT, I think, when I wrote it. But the last paper I had on this was last year. So I still
working on that one. But I think that's
about some randomized. So about the algorithm, it's just from last year maybe, and it's right, yeah. But I think these general problems of finding algorithmic proofs for some of these non-constructive arguments, so also something using, so there is some theorem that I like, that I call it combinatorial Nullstellensatz. So it's some algebraic geometry type things that has lots of applications. And this has lots of applications to problems that sound computational, and it does not give algorithm. And there also, each example gives you a possible algorithmic question. I don't, which we don't know to solve efficiently, and it would be nice. So if you want some specific example, let me.
Yeah, that would be good actually. These are, I think, it's the open problems in if there are some.
Yeah, actually, if you right, let's talk about this head guessing again, because we already talked about head guessing. So suppose, as I said, with linear functions, if the guessing functions are linear, they cannot even do four types of colors. Okay.
Yeah.
So this proof is algebraic. It uses this combinatorial Nullstellensatz. Suppose, let me ask you an algorithmic question. So suppose I give you this complete bipartite graph, n boys, n girls, and I give you for each of them a linear function. So each girl has a linear function of the colors of the boys, and each boy has a linear function of the colors of the girls. This is now a linear function over a field of 4 elements, let's say, okay? Yeah. Now, as I said, then this cannot work. Namely, there is some assignment of colors so that everybody is wrong. This is what the algebraic proof tells me. Can you find such an assignment of colors efficiently? I give you the linear functions. Can you find some color assignment on which everybody is wrong? We know that it exists because of the algebraic proof, but the proof does not give an efficient algorithm. And there are many examples like this. Maybe I'll mention one more. So this is some extension of the 4-color theorem. The 4-color theorem, it is known that it's equivalent to the statement that if I have a planar graph, and it is what is called cubic and bridgeless. So every degree is 3, every vertex has degree 3, and every edge is contained in a cycle, okay? Then the 4-color theorem, this is well known, it's an old result of Tate from the 19th century, that the 4-color theorem is equivalent, that each such graph, you can color the edges by 3 colors, so that no 2 edges, every color class is a perfect matching.
Yes.
So a planar, okay. Now here is a more general statement. Suppose I still want to get a coloring of the edges, but every edge now, so we have this planar graph, all the degrees are 3, and every edge is contained in a cycle. But now for every edge, you have a list of 3 colors, not the same colors, so it's called list coloring.
List coloring, yes.
So the first edge, you can color it either red or blue or green. The second edge, you can color it either red or yellow or black, and so on. So for each edge, you have a list of 3 colors. Then we could show, using this algebraic approach, that there is always a coloring from the lists. No matter what the lists are, So the four-color theorem is equivalent to the case that the lists are all the same list.
Yeah.
But if the lists are different, then still it is true. And this uses this algebraic approach, and it also uses the four-color theorem, because so we don't get a new proof of the four-color theorem. We use it, but you use it in kind of a strange way. You use the four-color theorem in order to show that some coefficient of some polynomial is non-zero. Never mind. So it's okay, but this again is an algebraic result. What about an algorithm? I give you such a planar graph. All degrees are 3, and every edge is contained in a cycle, and I give every edge a list of 3 colors. As I said, we can color properly from the lists. Can you actually find such a coloring efficiently? The proof does not give it. I mean, the proof of the original proof of the four-color theorem, of course, it's complicated, uses computers and so on, but it does give efficient algorithm. There is no problem. I mean, it gives a quadratic algorithm to four-color a planar graph, or to 3 color edges, right? But to color from the lists, we don't know an algorithm. We just
so I think so the catch is that, I mean, for color the list, I mean, then coloring from the list, like this color version, there is no polynomial time algorithm.
Right.
Is there any? I think exponential, of course, that you can get it.
Sure. Yeah, you can check
like k to the n or something like this. Yeah. But the question is, can we do it this one? And we know that there exists such a thing. There is like the such a thing is the
because of
colors.
Right.
But the question is that how can we obtain that one? There is one other problem that actually I wanted to find. I may remember it. This was another one that I will, if I remember it, I mentioned it. So I think these are actually nice set of problems that thinking about these problems, and I think that's actually a very good set of problems. And these are generally also open for a long time. So if the PhD students, I mean, you want to work on it or researcher, these are like nice problems to. I think probably also hard problems. You should not expect that you will get
right. So probably they are hard. I mean, maybe the question that we said about the necklace to find a larger number of cuts that will suffice. Maybe this is not. So this does not have such a long history. So so just to do the best that you can do. And as you said, it's the same. The cake. Some of the cake cutting problems. Are kind of similar, so these are, but of course these are not. I think they are not easy problems because at least I don't know. I don't know.
Great. So I think we talk about, I mean, a few of the topics. I think some maybe remaining topic. I mean, some other. I think you had. I mean, again, we cannot go over all things, but just a few other things. I think maybe you want to talk about. I mean, RS graphs. These are again one. I think these are some of the things that we talk about in magic in some sense, like the one that we mentioned about the hat guessing problem. That from the color of others, someone can find the color of. This is actually interesting thing. And the other one is like the same thing. This is both of them actually, they have this magic to me, the color coding theorem and the RS graph. The fact that even RS graph exists for this, I think you can define this. These are actually interesting, or the color coding, or other things that I think is interesting. And it would be good actually, if there are some main open problem also, other than finding this algorithm, please mention it, because I think that's the thing that the people can work on that.
Sure, yeah. Yeah, so some of those, okay, so let me mention something about the Ruja-Semredi graphs, because indeed I like it. It's and maybe indeed not everything is tight there. So the original thing was due to Ruja and Semredi in the 70s, and the important thing is that they realized this correspondence between dense subsets of integers that do not contain 3-term arithmetic progressions and some graphs that have some magic properties. And then there are different parameters of these. So let me mention this one version of the graphs that appears in a paper we had with Ankur Moitra and Benny Sudakov, because it really sounds pretty amazing that these graphs exist.
Exactly.
It's based on the same
amazing.
Right, yeah. So it's based on the same connections that Ruja and Semredi found between some geometric constructions and graphs, but the statement is as follows. So there exists a graph which is almost complete. So we have n vertices and almost every pair is connected. So I'll soon say numbers, but really almost, so you have 99.9% of the pairs are connected by edges.
Okay.
This one graph. And at the same time, you can partition all the edges into matchings, and each matching is induced. So a matching would be some part of edges that form a matching. No two of them have a common endpoint, and they are induced in the graph, namely on the subgraph induced on them, there are no other edges. You only see the matching. Okay, so all this, so you can partition this very dense graph into induced matchings, and every matching is of size n to the 1 minus little 1. So very big matching. You see, if you have even one matching of size n over 2 that covers everything, then you are not allowed to have any edges whatsoever, right? Because it
exactly, that's exactly the beauty of this. So when you try to construct it, I think when you mention there is a bond, but when you try to construct it, oh, how come can I add it? As you mentioned, n over 2, you cannot add any other edges essentially.
So it looks, and the matchings are pretty big. So it looks that almost all edges are missing, right? Because you have these huge matchings, and then they are induced. So it looks as if almost all edges are missing, but in fact, almost all edges are in, right? So almost all, and this has, because it's so strange, it has some nice applications to radio network, to the graph test in the PCP theorem, and to some, so it somehow has, but just because it is surprising, and I think that still in this type of graphs, there are several parameters. So it's not understood what is a tight connection between the parameters. And then the constructions, once you decide what to do, is not difficult to describe. So but it's based on some high dimensional geometry. So some measure concentration, but indeed it's very surprising. So this is a Ruja Semredi graphs, and as I said, some bounds there are still completely not understood. So some parameters are relevant to what's called the triangle removal lemma, where there is a huge gap between upper and lower bounds, or it is related to Barron construction about the maximum density of a subset of the integers between 1 and n with no 3-term progression, on which also...
I think even the bond, the exact bond or the number of edges of these graphs also is not completely settled down. We know upper and lower bound, but it's not completely...
No, it's not. Yeah, there is a big gap. So somehow if you have so again, I think it's a difficult problem, but maybe let's say the following. Suppose you have a graph in which, this is one simple way to state it. Suppose you have a graph on n vertices, and every edge is contained in a unique triangle, in one triangle. Every edge is contained in one triangle. Okay, so this is some property of the graph. And the question is what is the maximum number of edges you can have in such a graph? A graph in which every edge is contained in one triangle, in exactly one triangle. So it is known that this maximum is bigger than n to the 2 minus epsilon for every epsilon. So it is pretty dense. So that follows from the Barron construction. And on the other hand, it is known, so this was proved basically by Semredi or by Ruja and Semredi, that it is also known that this maximum is little of n squared. So it is not more than, right? So it is more than n to the 2 minus epsilon for every epsilon, but it is less than epsilon n squared also for any epsilon, if n is big. But to understand, the bounds are between n square over log star or something is the upper bound, n square over log star of n, and the lower bound is something like n square over 2 to the square root log n. So there is still a very big gap between the upper and lower bound, and it's related to several questions in number theory and in property testing. It's kind of it's interesting to understand it. Again, I think it's a very difficult problem, but it's a nice problem.
Yeah, I think I wanted to add, actually, this is the one that I remember. So this is another problem that essentially use topology, or essentially, I think topology that we are considering like the different surfaces, not just plane, torus, and other essentially genus things, or like some others, as you mentioned, algebraic geometry that talks about polynomial things, and we don't know the algorithm for that. I think another famous problem that he had actually a paper with Christos Papadimitriou on that is about the, I think, Giordi-Lovaas theorem that I think you should, you know probably that as well, that you have a graph of k-connected graphs, and there are the numbers n1 to nk is given to us. And we know that we can also, there are k-connected graphs between any two vertices, there are k-disjoint paths. And we can actually, the theorem says that if you give me n1 to nk, these are the numbers that their sum is equal to n, I can divide this subgraph into disjoint connected subgraphs such that the size of the first one is n1, the second one is n2, and others. And each of them is connected. That's actually another one actually uses this kind of the...
It is this, and even you can force each of them to contain a pre-specified vertex. So you
exactly, and pre-specified vertex.
Exactly. Right,
and
so that's it. Right, so this is another example. There, actually, it's even more, so there are two different proofs, because the proof of Lovaas was topological. The proof of Jerry was combinatorial. It's kind of a augmenting path type argument, a complicated augmenting path, but the way it is described, it's exponential process. So it's not clear. I mean, it kind of looks more like an algorithm, but the algorithm may take exponential time as far as we know. And indeed, in this example, we also don't know how to find it. Efficiently. We know to find it efficiently for k equals 2. So that would come from a ST numbering of a graph, but for the special case of 2, but not for larger.
Exactly.
It's also...
We had some approximation for that, actually. It was some still working paper on that one. Great, so that was the thing. So I think you want to also mention color coding. I think that's also another magic that I use it in some big parameter. And
yeah, because also that's very easy to describe. So let's say the original problem is to, suppose we have a graph, an input graph. It's an algorithmic problem. We have an input graph. We want to decide if it contains a path, just a simple path of length k. Okay, so we want an efficient algorithm, and we can extend it to more, but let's just think about this case. And the interesting case would be that k is equal to log n. So you want, because this was a specific question of Papadimitriou and Giannakakis, I think. The question was, can you do it in polynomial time or not? Okay. And what we realized is that you can do it in polynomial time. So that's in a paper with Euster and Zwick. And the description of that is, so in general, you can decide if a graph contains a path of length k in time, which is exponential in k, something like maybe 2 to the k or 4 to the k, times the polynomial in n.
So, I mean, you are doing some kind of branch and bound backtracking, correct?
No, so I'll tell you exactly what we do. So that turned out to be useful in parameterized complexity, right? Yeah. Because this is, but anyway, so here is actually the algorithm. It's very easy to describe it. So you first describe it as a randomized algorithm. So the randomized algorithm, you color the vertices randomly by k colors, okay? And you hope that if there is a path of length k, say k vertices, you hope that each of them get distinct colors. Now this happens with probability k factorial over k to the k, which is only exponentially small, 1 over e to the k roughly. So if you will do it exponentially many times, you will get it.
You get it. So essentially, when you boost it, you can't do that. But everything is dependent on k, essentially.
Yeah, okay. And now we want to find if there is such a path. Now it's already a graph that is colored. And we ask, is there a path in which all the colors appear, everyone exactly once? And this you can do by dynamic programming. It's not difficult. So basically, you can do it in dynamic programming with dynamic programming in time 2 to the k times n, or 2 to the k times n squared or something, right? So this is basically already a randomized algorithm. And then the nice thing is that you can de-randomize it. So you don't really need to use probability. To de-randomize it, just by the way I describe it, it's enough to find a polynomial number of coloring of the vertices by k colors, so that every set of size k in at least one of the colors gets distinct colors, right? Because then you will try it for each
of them.
Yeah, and this, it turns out that you can do it by some explicit hashing schemes. So to describe it completely, it takes some time, but I mean, the nice thing is that the algorithm, if you look at it, you implement it, I don't know, it will do some things that look totally irrelevant. It will compute some polynomials over a finite field, and it will do these hashing things that looks kind of irrelevant, and then it will do this dynamic programming, and still it will work. And then it turned out, so this is like the simplest case of the color coding, and but it led to quite a lot of additional things, and because it's useful in parameterized complexity and also maybe in computational biology, when people wanted to count, you can also count or approximately count how many paths of length k the graph contains. And it's not only for path, you can replace path by cycle, you can replace it actually by any fixed graph with a bounded tree width. So it's kind of...
yeah, that's actually a beautiful term. So you called it color coding.
Yeah, we called it color coding because it looks that it's like you color code the vertices by the coloring, and then you use it to kind of find this this multicolored.
Yeah, I think that's a beautiful, theorem. I use it that again. This is one of the other things that when you think, there's okay, it works. But when you try to use it, we actually use it to get a very general set of fixed parameter algorithms using this color coding. Actually, we can get the result. And this is very like a beautiful algorithm. You want to find the path of length k, you don't know. This problem is, if k is large, it becomes NP hard essentially. We don't know how can we do it. But then for a small k, what do? You just, color these guys randomly, and then you just do some dynamic programming and solve it. That's actually a beautiful algorithm, understand? But the idea again, but the one that if you want to de-randomize it and use this other, essentially polynomial things, then becomes, more involved. But it's still, very interesting that all of them, I think that's the thing that I mentioned in the announcement, that how interestingly, this, you actually bring this kind of the things from algebraic geometry, from topology, and then make it algorithm. I think that's a beautiful, very beautiful set of results. Is there any open problem here for this problem?
Yes, I think, people kept improving. So in parameterized complexity, you want to get c to the k times a fixed polynomial, and you want c to be as small as possible. You see, it is clear, if you believe the exponential time hypothesis, it is clear that you cannot hope to do better than that, right?
Yes.
You cannot
exactly.
in polynomial time, right?
You cannot get square root of k.
But you want to get a smaller c, and then there were pretty clever things. So people were using exterior algebra. There were some very nice things that went into that, and then maybe it still would be nice to decide what is the best thing you can do from a parameterized point of view, like what is the best c, so that the algorithm will be c to the k times the polynomial in n, and then you want to extend it from paths to cycles and to so we were working also on you want efficient algorithms to decide if a graph contains a cycle of length k. How efficient is it for every given k? What is the best that you can do? And it's kind of understood more or less for small values of k. It's not completely understood for bigger k's, and then it is closely related to specific questions in parameterized complexity. You know, even people do not know how efficient is it to decide if a graph contains a triangle.
Yeah, exactly.
So this is basically matrix multiplication. We don't know,
yeah.
But
yeah, exactly. That's like I mean, or this is even for the threesome, we don't know whether n square is the best thing or not. Great. So I think maybe just saying for this type of research thing, any other areas that you want to mention that we missed, of course, a lot of papers, we cannot have everything, but important one. And also, among the open problems, also to finish it, are there any, like, if you, somebody asked, what are the 2-3 most important problems? Did we mention all of them, or still there are some other open problems that you will mention that, and sometimes you wish to that they will be solved essentially soon, maybe not soon, but soon, yeah.
Okay, so in terms of areas or topics that we didn't mention, I'll only mention the buzzwords. So really, I worked a lot for many years on expanders and all kinds of applications of expanders. So I just mentioned that this is something on which I worked a lot, but so these are sparse graphs that are highly connected and have many applications, and they have connection to the spectrum of the graphs, but I just mentioned the buzzword, and maybe there was some conjecture of Hadwiger and de Bruyne in combinatorial geometry, but let's again leave this just as a word itself.
I think this RS graph especially and expanders, these are like the most, I will say, magic graphs that somebody can.
But expanders are more, so they are also magic maybe, but they are more sparse, right? So
exactly. So, but I think obviously, to magic graph that if you want to work, if you want to work essentially for planar graphs, I think planar graph, bounded or velocity graphs, these are for the sparse graph. But so expanders, I think, goes still a sparse graph generally, but it's hard, and then they go to RS graph that becomes complicated. These are like the
That's right. So they look random.
Exactly.
Right. Okay. So in terms of problems, so there are the problems that I would really want to solve, but that are probably very hard, right? So probably one of the most interesting problems, and only in the old days I was working on it a little bit, but is to find bounds for circuit complexity of things, right? So this is related to PNP, but even if you are not, of course, we would all like to solve the PNP problem, but even if not, so just to prove some mild lower bounds for circuit complexity shows that any Boolean circuit that solves, the clique problem needs to be of size at least cubic, at least. So just to get, so there are these bounds for monotone circuits, but but in general, there are basically no non-trivial lower bounds, and and there are even some reasons to think that it's hard to, because of the connection to natural proofs and so on, that maybe it would be hard to prove such things, but this is a very concrete problem, and this is would be very nice. Then there are these problems that I mentioned about finding algorithmic versions of existing theorems that are proved using some of those algebraic or topological tools. And there are many examples like that, and it could be that some of them are not. Maybe some of them are not so difficult. I don't know. I mean, I can think. So still,
so essentially, this problem that we already discussed about, getting algorithm for this.
Yes, so some of them we discussed. There are others as well, but and then in terms of major problems in discrete mathematics, there is this sunflower problem of Erdős and Radon, which there has been some major breakthroughs recently, but it's still not completely solved. There is
the sunflower
problem that also has many connections to, and the problem that I thought about on and off for quite a while. So it's a Ramsey type. It's a combinatorial problem, but it's also equivalent to some question on Shannon capacity of graphs, which is natural in information theory. But let me just state it as a combinatorial problem. It's equivalent. So this is a Ramsey type question, and this is what is the maximum size, maximum number of vertices of a complete graph so that you can color the edges, not a proper coloring, you can color the edges by k colors with no monochromatic triangle. So you don't see a triangle of the same color, you have k colors, and we want to color all the edges of as big a complete graph as we can. So there is, the lower bounds are exponential in k. A simple lower bound is like 2 to the k, but there are better ones. So 2 to the k is whenever you add a color, you take 2 copies of what you have already, and the bipartite graph between them, you color in the new color. So since it's bipartite, there is no triangle, and also there is no triangle here, and this would give 2 to the k. But there are actually constructions that give about 3.2 maybe to the k, something like this. And the upper bound is more than exponential, so it's something like k factorial. And the main question here is it exponential or is it more than exponential? And somehow for the question in the Shannon capacity, you really take the kth root of that. So the natural question is if the kth root of that is finite or not. And therefore, the gap between exponential and more than exponential is kind of the interesting thing. And this is also an interesting problem, I think.
Yeah, great. Yeah, I think that was like a great thing for the research. I think when we make you just, I think few more questions, and I think we are done. This is like non-technical question. I think maybe this is the vision also that would be nice. So I think like one thing you mentioned about the administrative work. I think that is also another thing. There are several people working on theory or non-theory. They took like administrative. You were the chair of the I think the CS department, as you mentioned. And generally, did you take other administrative work? And how do you think about administrative work? Like, what would be the things? Are you plan to take more? Or like you feel that okay, I'm going there, then I cannot maybe do my research that much, and I feel that happened to me actually sometimes that I went to industry. Yet took more time. I thought I couldn't publish in this year that productive or something like this. Yeah.
Yes, so I do some administrative things in the, like program committees or prize committees,
Yes, exactly.
and so on. But this is not. I don't plan to be a dean or something. So this really is. I mean, I did it, as I said, for 2 years. It was very, very time consuming. I think it was more or less okay. So maybe I mentioned that my main duty was at that time they wanted, like in many universities around the world, to separate the computer science department from the mathematics department. In many other places, computer science was part of engineering, but in Israel, traditionally, it started with mathematics. And somehow the perception, so I had a joint appointment in both departments, and I have good relations with both. So somehow the assumption was that I'd be able to do it peacefully. You have to split budget, you have to split, and it was, so splitting the budget was easy. It turns out that splitting the real estate, the office space, is a very, very difficult thing, and that really took years, and it's so it was challenging. I think I was basically okay, but probably I don't see the time better in this than other people, and I probably don't. I think I've done enough of that. But so taking, but still, I mean, we all have to do some administration. I think this is part of our duty. So as I said, I mean, being an editor, serving on some prize committee, doing things like that. These are things that I still do.
Yeah, and I think, I mean, this is the important one. I think that is, like we were talking actually, I think with Professor Madhusudan as well on those stuff, that I think these are the things that in some, as you mentioned, I think exactly that we should take these administrative things, like for example being the chair or others, because like generally, I mean, very strong researcher, I mean, like yourself essentially, that would be great. I mean, because that person would be the face of the department or face of the college in some sense. And at the same time, it is always, I will say that the best person is the person who does not want to take the job. Like, because I think for that person, I mean, there are other options. So it's like he wants to actually serve and make something improve, not promote himself in terms of management as this one and become a boss. And generally, I think I have experience, I think I'm sure you have experience, that the people that they want to make a career out of it, and that's like, then they want to be boss of others. This should be not the case. It should be more like a service provider to others if you become the chair or the dean, not that you are just going there to promote yourself. I mean, of course, if you do a good service, that may happen as a natural consequence of that. But if you go there and you want to be the boss, I think the people will be unhappy about it. And
yeah, no, I think, I mean, I still admire people who are willing to do it, and it's fine with me if part of the motivation is also personal, but definitely part is also, it's your incentive to do a good job as an administrator, even if you view it partly as a mean to promote yourself, but still, the way to promote yourself would be to do a good job and make sure that your department will be excellent and will. So the two things are not contradictory, and I think it's okay. And there are people who are willing to do it, and some people are very good in doing these things well. But there are also people who do not want to do any of this at all, which also is okay. But I think, I mean, I view it that I've done my share, and I would still do some things, but not things that require really years of service. I mean, to really be a dean or it means that for a few years you basically don't do research at all, and this is not something that I mean, I don't know how many years I still have left.
Yeah, exactly. Yeah, I had the same feeling essentially. Like for a year, I was like Amazon. Oh, this my productivity went down. I feel bad about it and should do this one. Yeah, I think that was the thing. So, do you want to add? I mean, anything also about the industry versus, I mean, academia? I think you have maybe a few words you want to say, and then I think.
Yeah, so it's, I mean, as you said, I've been, I spent some time in several, in IBM. I was once in
Microsoft a lot, I think.
I was
met you a lot.
Microsoft, in Bell Labs, in Bellcore. So that's interesting, and I think now the connection between industry and academia, because of all the high tech, is pretty close. But I'm more on the theoretical side. So always, even when I was in Microsoft or in Bellcore, Bell Labs, I was talking mostly with the theory people. And actually, if we talk about industry, I was even at some point during the bubble, you know, at some point everybody was kind of involved in some startups.
Exactly.
So in around 2000, I was also involved in as a co-founder in one
a startup,
some company of security, and even and maybe and it even this company for many years it kind of existed, and then it went public actually in 2018. So it was. So this had something to do with security. After 5 years, I was less involved in it, but it was.
But you were the founder of that company, actually.
Yeah, but I was a co-founder, but it was diluted many times. So
yeah, of course.
Still, it was something. I mean, because and then it went public, and then it was afterwards. After it was public, it was even bought by and it became private again. But that time, I was not really involved. But still, it was really an interesting experience to see how this goes, and to see it also from the investment point of view. You know, so for a while I was also talking with venture capitalists when we got investments, and it was kind of interesting, but not. I was kind of. Although I was one of the co-founders, I was less involved directly.
And so, yeah, so that is interesting actually that you went through this VCs as well, because that's a different world essentially, completely different world.
Yeah, it was still interesting to see how it goes, and then of course, I mean, you know, when the bubble collapsed. So as I said, for many years, this company was kind of struggling, but finally it succeeded somehow. So much.
Yeah, so that's, yeah, congratulations. That went public. And so one question: have you ever written code? I mean, like maybe after your study, like undergrad or grad or something.
So you know, as I said, I've been like a research officer in the army for 4 years. Yeah. So then I wrote the code a lot, but
I see. But not after like getting your PhD.
Basically, not after. I mean, sometimes my co-authors were. Now I think I cannot. I haven't written for many years, but it's useful. I mean, so often some students are doing it, and it often gives you some intuition on what.
Yeah, actually, I think Python is actually very nice code. I mean, I don't know. You probably have done it before? You have with C or C++ or something. I mean, actually, that C++ also became more like Python, because Python came. There are lots of structures that Python added, and they added now to C++ too, and is like there are lots of structure that Python added. But Python actually is very Yeah,
but I'm so old that when I programmed, it was in Fortran. Can you imagine?
Yeah. Okay. So that was before that. Yeah. The Fortran was before that. Right? Yeah. But yeah, I think actually basic. I mean, the Python is a very nice abstract thing. I have actually, it was interesting. I was the like chair of the search committee last year, and then I got these people essentially. The people voted essentially. And the list was like, I don't know, 200, 300 people that they needed to select some of these people. And then I have written, so okay, I needed to get each of these persons in a few rounds and count the number of votes, etc. So I just got actually a Python program that reads this one, the whole things, and these votes and count it. But also there was like, especially for string matching, etc., is much easier than others. But yeah, so that's actually Python is a good one if you, at some point, if you want to do some very easily, you can actually write that type of stuff. And I think last, probably not least, I think message for the high schoolers or like the people who want to do math, computer science, what they should do. I mean, they're high school, the middle school, and they want to do, great mathematics, what they should do. Should you go like programming first, do math? Yeah, anything advice?
Yeah, so all of those are, I think that my only maybe short advice is that it's very important to do what you like, and to like what you do, because if you love your occupation, then you there are more chances you will be good at it, and actually, we really spend more than half of our time in life doing our work. So it's very important to like what we are working in, and not to think too much of what to try to choose an area that will be practical or will be useful. If you are good at what you do, you will find your way. So if someone in high school that is interested in computer science finds that programming is what he or she likes, then this is fine. If it's theory, then this is also fine. But it's important to be curious about what you're doing. And in general, of course, computer science now is a great area, both practically and theoretically. It has fascinating problems. It's really changing the way the other scientific and actually all academic areas are behaving. Like the more computational and algorithmic point of view now appears everywhere. So somehow to be interested in computer science, in mathematics is a great thing for people that like to do it.
Great. Yeah, I think thanks a lot. I think I enjoyed a lot. I learned a lot, and hopefully people, who will watch this one over all media and also in the future, because it will be, everything would be on the YouTube as well as other things, and also on podcasts. So, and this is, I think, one thing that we have, we don't have any slides, we just talk. So they can listen when they drive or they walk or they exercise, anything. I think that would be a good thing. Thanks for your time. I think that was a great things. If you have any final things you can say, otherwise we can.
No, I think, we did, so now it's 3 hours.
3 hours.
Yeah. So I only, I enjoyed it, and let me thank you for indeed this initiative and for investing so much time in organizing this thing. It was nice.
Yeah. Thanks a lot. So bye everyone and the audience. Thanks a lot.
Bye-bye.
Bye for now.
Thanks. Bye.